So we've seen how we can use multi-category explanatory variables to recreate one-way Ancopa. Just like with binary explanatory variables, we were able to recreate the two-sample t-test with equal variance. Now we're going to make it more interesting and add one of those continuous explanatory variables and see how we can use these multi-category qualitative explanatory variables to test for differences in regression lines. So let's do that. Let's create a new explanatory variable, x4. Let x4 be the continuous nitrogen level in the soil. Okay, and let's fit a model. Y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus epsilon. What will this model look like? Well, the expectation of y, right, is just going to be this part here without this epsilon, and that's what I'm going to draw here. So if we put on our x-axis x4, let's say that beta 4 is positive. So there's a positive relationship with the expectation of y, corn yield, and nitrogen level. We might have something that looks like this. We'll have 4 lines going up, and they're all going to be parallel. Okay, because slope for all 4 groups is beta 4. But the intercepts vary. So right here, well, it could be any of these. So let's say, let's just throw in some numbers here. Let's say like beta naught is something like 5. Beta 1 is, let's say, -2. Beta 2 is -3. And beta 3 is +2. Now, let's say this is 5. Okay, and this is going to be beta naught. All right, our intercept. Now, x1, let's say, is going to be 2 less than that, so this would be at 3. And this distance here is going to be beta 1. Okay, the difference between beta naught and beta naught plus beta 1 gives us the intercept for this case. So x1, that was Wisconsin, so this is going to be Wisconsin. This case, just the base intercept, this is going to be Illinois. So let's say, okay, let's do this one is x2 is 1, where x2 is 1 and x1 is 0 and x3 is 0. That's the Minnesota case. Okay, so beta 2 is the difference between the intercept for Illinois and Minnesota. So it's 5 plus -3. So the intercept for Minnesota is 3 less than the intercept for Illinois. So this would be our Minnesota here, and this here. So this guy is at 2, and this would be beta 2, this difference. And then from here to here, this is going to be our beta 3. This is 7. This is the line for Iowa. Okay? So this is just hypothetical. Imagine that these are the differences here. So we've got 4 lines, and their slope with regard to x4 is all beta 4. So they all have the same slopes, but their intercepts vary. Okay? So that's the idea here, that we have parallel lines because the slopes, at least with regard to nitrogen level in the soil, slopes are all the same, but the intercepts are varying. Now I'm going to show you a more complex case where we're going to allow for the intercepts to vary and the slopes to vary. And this is where, if you understand the binary case, it should be straightforward, but if you don't understand the binary case, it will be a little confusing. So please make sure you understand the binary case. So what if we could fit this model? Y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus beta 5 times x1 times x4 plus beta 6 times x1 times x2 times x4 plus beta 7 times x3 times x4. Okay. So, what does this model mean? So, the interpretation of our betas remains the same. These are the differences, beta 1, 2, and 3 remain the same. The differences in the intercepts for the different states. So let's keep Illinois blue, and let's go this color for Wisconsin. So this would be Wisconsin, beta 1, so intercept, diff. So from Illinois. And here we have x1, which is our, when x1 is 1 and x2 is 0 and x3 is 0, that's going to leave us just with, that's the Wisconsin case. So this here is going to reduce to x4. Okay, and we're going to have, for the effect on of nitrogen on corn yield, we're going to have beta 4 times x4 plus beta 5 times x4. And just as we saw in the case with binary, what this ends up doing is we can draw out the x4 and we have beta 4 plus beta 5 times x4. And so beta 5 ends up being the difference in slope with regard to x4, nitrogen, between Wisconsin and Illinois. Beta 4 is our slope for just the Illinois case. This is because when x1, x2, and x3 are all 0, that corresponds to the Illinois case. So I should write that in here. Slope for Illinois. So beta 5 is the difference between the slope for Wisconsin and Illinois. Beta 6 let me get my colors right? This is the slope for Illinois. So let's look at the Minnesota. Here, for beta 2, it's the diff in intercept between Minnesota and Illinois, and beta 6 is going to be our difference in slope between Minnesota and Illinois. I'll explain again why that is. When we have the Minnesota case, x1 is 0, x2 is 1, and x3 is 0. So this term goes away, and this term goes away. And we have, it reduces to, with regard to the slope part, x4, beta 4 times x4 plus beta 6 times x4. Beta 4 is the slope for Illinois, and so we have this adjustment to the slope, which is beta 6. And that is the adjustment in the slope when we have Minnesota data. What will this plot, and then to extend that, beta 7 is for the difference in slope between Illinois and Iowa, and beta 3 is the difference in the intercept between Illinois and Iowa. What would a model like this potentially look like? Well, it's going to have varying slopes and varying intercepts for each group. So we might have a model, well, let's say we might have this Illinois case, we might have this Wisconsin case. Well, it's probably not going to decrease. We might have Wisconsin case, we might have Minnesota case, and then let's say we have some Iowa case. Okay, so you have varying slopes, and varying intercepts. Just like in the binary case, fitting this model is the same as fitting all 4 models completely separately. You'll get the exact same estimates for your lines. What's different here is that it allows us to test for relationships between the lines. Test if the lines are different. We can test, is the slope for Illinois different than the slope for Wisconsin? That would be testing if beta 5 is 0. That might tell us if nitrogen has a stronger effect or a weaker effect or something like that on corn yield in one state versus another. We could test if the intercepts are the same. That doesn't really make a lot of sense in this case, since 0 nitrogen in the soil isn't a realistic type of scenario, but it's something you could test if you wanted to. And you can test if the slope terms are all equivalent. So do all these models, do all of them have the same slopes, or do they not? There's quite a range of hypotheses that are possible. Again, using our additional sums of squares toolkit to do this. One final model that I'll show you would look like this. Y equals beta naught plus beta 4 x4 plus beta 5 times x1 times x4 plus beta 6 times x2 times x4 plus beta 7 times x3 times x4. And I'm using betas 4, 5, 6, and 7 just to keep you consistent with what we saw before, but they could be named anything. What does this model look like? Well, here in this model, we have omitted the terms that allow the intercept to vary, but kept the terms that allows the slopes to vary. This model is going to look like this. We're not going to allow the slopes, we're not going to allow the intercepts to vary. They're all going to have a fixed intercept, but the slopes could potentially vary. So this is a varying slopes, same intercept model. Okay. So that's quite a lot, and I hope that it's been a relatively reasonable extension of the binary case. There's a lot more coefficients that get added in, and it can definitely take some time to figure out, well, what do they all mean? And I highly recommend sitting down and writing out your model by hand, exploring what happens when you plug in possible values for these indicator variables and how the models simplify in order to gain an understanding. I especially recommend that you do this by hand before you try fitting these types of models in R. It can take a little bit of practice to translate these ideas about varying intercepts, varying slopes, and so forth into the R syntax, and it's very easy to make a mistake or fit a model that's something that isn't what you think it is. So what are some I'm going to kind of wrap up here with a couple remarks. So, other extensions. We've shown the case where we just had one continuous predictor variable, but you could have multiple continuous predictors. So imagine, like, it's not just nitrogen that varies by plot, but maybe irrigation or something like that. And then you could have, like, you kind of have what you might call two slopes. One slope with regard to nitrogen and one slope with regard to water or soil moisture. And both of these can vary by location. So it's basically, instead of comparing lines, now it's like you're comparing planes. And that can get pretty complicated. So you got to make sure that you're understanding what's going on. And you can also have interactions between continuous predictor variables. So up here, when we multiply the indicator variable by the continuous variable, that's what's called an interaction. There's an interaction between the indicator and this continuous variable. It's also possible to have interactions between continuous predictors. So there could be an interaction between available nitrogen and soil moisture content. So that can make it a little bit more complicated. And then I'll just finally wrap up with just a short note. If you're hanging out with kind of old school people, you might hear the word Ancopa talked about, and this is what's called Ancopa, analysis of covariance. It's basically where you might have varying intercepts but the same slopes. But this includes Ancopa and allows for some even more complex types of analyses. So If you hear someone talk about Ancopa and you understand this, then you understand Ancopa, but it just might be using terminology that you're not quite familiar with.